Hello everyone, a very good morning, and I hope everybody is doing great, right? And you should be doing great no matter what, right? So a lot of new names because it is going to be a question paper discussion class, right? So I see a lot of new names: Ankit Ram, Sujit, who else? Rahul Krishna, Akshaya Sri, Anish Karthik. All these are the new names which I'm seeing, right? It's good to connect with all of you. Ananya is again a new name, right? Ananya, I think she was in my class. Anyways, so it's good to see that new people are here, right? So maybe I think this is the first class. Maybe for some of you, this is the first time you're even seeing me, right? So for those of you, my name is Akash, right? So and I am handling chemistry for your current batch, but not for 1 second. Just give me a moment, people. Just give me a moment. Okay. I'm so sorry, people. Like that was a very important call and I had to attend it. Okay. So yeah. So I see so many people, right? So without any further delay, let me share my screen. Okay. So I hope my screen is visible. Right. So this is 12th and today is 3rd of October, right? Uh, but before this, let me so this was the question paper, right?
Yes, sir.
Right. Okay. So we will solve all the questions, right? Okay. Fine. So first question. Right. A compound is formed by elements A and B crystallizes in cubic structure, right? Where A is at the corners, very important, where A is at the corners of the cube and B atoms are at the face centers. What is the formula of the compound? Right. Now, for these kind of questions, how will you approach this is very simple, right? So when I have a cube, okay, please bear with my drawing. Okay, so when I have a cube, when you have the atoms at the corners of each cube, people, right, all the 8 corners, if you have, say, all these are A atoms, right? Now, what you have to understand is this is one unit cell, right? This is one unit cell. Now, please understand from one point, right? From one point, any vertex, I will be able to draw 8 other cubes. At least this particular point can be shared among 8 other, or say 8 unit cells. Or I don't say 8 other, 8 unit cells. And this is one of them. So basically, along with this unit cell, from each and every point which I have mentioned here, right, it is going to be shared among 8 unit cells. And this is one of them. So rest 7 is remaining. Okay, so now if I ask you, if I have a vertex, right, vertex means the corners. Okay, now what is the contribution to one unit cell?
1 by 8, sir.
Exactly, right? The contribution of this particular point to this unit cell is 1 by 8. Okay, now obviously what you have to understand is 1 point contributes 1 by 8. How many such points I have? Obviously I have 8 points, right? So obviously what I'm going to say is I have 1 A atom per unit cell, because all the corners I have A, right? All the vertex points I have A, and the contribution of one of the vertex point is 1 by 8, and I have 8 such things. So I have 1 A atom, right? Now that is what is given in this question. A atoms are occupying the corners of the cube, right? Now what happens to B? B is at the face center, right? Face center means what? Say if I take any one face, say if I take some other color, and if I take this particular face is one square, I can have 6 squares. Hope you all know, right? A cube contains 6 squares. Combining together forms a cube, right? Okay, so if I take one face, at the center, if I just draw it like this, at the center of this face, I'm having B. Right? Now, what you have to understand is, people, say, assume that this is one face, right? This is one cube, what I have mentioned here, right? At the center of this cube, I have a lattice point. That is where, this is where my atom is present, right? Now, it is very easily you can understand this particular cube can be a part of, sorry, this particular face can be a part of 2 cubes like this. Or if at all you are worrying about what exactly is happening, see, you take 2 rooms. Okay, your room and the next room, right? Now there'll be a wall connecting your room and the next room, right? There'll be a wall. Say if you have 2 classrooms, next classrooms, there'll be one wall which is connecting both these classrooms, right? And that's exactly what is the knowledge you have to understand, right? So this particular face is shared between 2 classrooms, and classroom is nothing but a cube, right? So that is exactly what you have to understand. Right. So now in each of the face center, right, I have 6 faces, right? And in each of the 6 faces, you have 1 B atom, right? And I know for one face, the contribution is what? 1 by 2, because I told you that this particular face is shared between 2 cubes, right? Now, how many such faces I have? I have how many faces? 6 faces. Right, I have 6 faces. I told you 6 squares make up 1 cube, right? So obviously the total number of B atoms is 3, right? So I have 1 A atom and 3 B atoms. So easily I can tell the formula as AB3, right? I can easily tell the formula as AB3. I hope everybody is understanding, right? Face center means the contribution is 1 by 2, and I have 6 faces. Vertex means the contribution is 1 by 8. I have 8 such points, right? So like that, you'll be able to calculate that the answer to this question is A, B. Okay, very, very easy. Right. Okay. Going to the next question. Right. An element has a body-centered cubic BCC structure with an edge length. Cell edge means A. This is A value. Okay. When they give you, when they mention radius, then it is R. But if they mention edge length, cell edge, all these represents the A value. Okay. Now all you have to know is the formula. Right. So now for your simple cubic, what is the relationship between A and R? Can I tell?
R is equal to A by 2.
Exactly. R is equal to A by 2. This is for simple cubic. Right? And say if I go for BCC, body centered cubic, what is the relationship?
R equals root 3 by 4A.
Exactly. Root 3 by 4A. For FCC, what is the relationship?
A by 2 root 2.
R is equal to A by 2 root 2. So this formulas alone, if you remember, all you have to substitute is substitute the A value or R value, depending on the question, whatever is given to you. Right. Now they have given us that this is going to be a body-centered cubic BCC structure. So obviously I know the formula is R is equal to root 3 by 4A. Right. So now what is the answer then? A is 288. The answer is G. Root 3 by 4 into A is 288 picometers. Very easy, very easy. Okay, moving on to the next question. The sharp melting point of crystalline solids is due to, right? We'll look at all the options. This is a theory question, so we'll look at all the options. It is because of the regular arrangement of constituent particles observed over a short distance, right? No, look at this. A regular arrangement of particles, constituent particles means whatever the particles are there, right? A regular arrangement of constituent particles observed over a short distance. Is it short distance, people?
No, sir. Overall, sir, long distance.
Overall, it is perfectly arranged. It is perfectly arranged. Everywhere you see, it is perfectly arranged. So this first of all is not even a correct statement, right? This is first of all is not even a correct statement. So obviously this cannot be the answer, right? Okay. Same arrangement of constituent particles in different directions. Different arrangement of constituent particles in different directions, and at last, the regular arrangement of constituent particles over a long distance in crystal lattice. This is a correct point, right? But we don't know whether this is the answer to this question. Anyways, so now you see, we will look at these 2 points. Same arrangement of constituent particles in different direction, or different arrangement of different arrangement of the constituent particles in different direction. Which of them is correct? I'm not asking about the answer. I'm asking about which is the correct statement.
C is correct, sir, because crystalline solids are anisotropic.
Exactly. This is what is meant by anisotropy. Right? Different arrangement of atoms, different arrangement of constituent particles in different directions. Right? That is what if you measure, say, refractive index in one direction, say a direction A, and you measure the same refractive index in direction B, you might end up with 2 different values. Right? That is what is called as anisotropy, but that is not the answer to this question. Right? Now, why is it that they have proper melting point, sharp melting point? What do you mean by sharp melting point? 0 degrees means 0 degrees. But if I take an amorphous solid, it will be a range of temperature, say 0 to 10 degrees Celsius, 10 to 20 degrees Celsius, like that it will be. When I say sharp, a particular melting point, at that temperature, perfectly it melts. Right? Now that happens because of regular arrangement of constituent particles observed over a long distance in crystal lattice. That is the answer to this question. Okay. Now this is a correct statement. C is a correct statement, but this is not the answer to this question. Okay. A and B are absolutely wrong. That is not even a correct statement. C and D are correct, but for this question, D is the correct answer. Okay. Fine. Next question. Which of the following is a network solid? What is a network solid?
Covalent solid, sir.
Okay, it is a covalent solid. All you have to understand is network solid means covalent solid. Right? Now, SO2 is going to be only single monomer. H2O is not covalently attached. See, understand that H2O is again only this one. Right. Now, between 2 H2O molecules, I can have hydrogen bonding. That is okay. right? I can have hydrogen bonding between two water molecules, but this is not covalent. This is hydrogen bonding, right? But if you take diamond, I can have all the carbon atoms you see are covalently linked with each other, right? So the answer to this question is diamond. Why is it that all answers are coming B? I really don't know. Anyways, okay. So when I say a network solid is nothing but a covalent solid. Covalent solid means the entire whatever be the constituent particles are held together only with the help of a covalent bond. And that will happen only in diamond. We all know that. We have been studying about from our lower classes. Right? Okay, fine. Next question, moving on. Right. The type of stoichiometric defect shown by Z and S.
Frankel, sir.
Okay, right. So like we all should understand what do you mean by Frenkel, what do you mean by Schottky, that we are not going to spend time. Everybody knows what is Frenkel and Schottky. Anybody wants me to explain what is Frenkel and Schottky defect? I hope everybody is fine because you must have prepared for your exams. It is very easy to understand. Okay, so now all you have to understand is Z and S. Like for everything, you will have some examples for each. The first thing is you have to understand what is the defect, right? What do you mean by Frenkel defect? What do you mean by Schottky defect? What do you mean by metal excess? What do you mean by interstitial? All these things you have to understand first. Okay, right. Now, once you understand that, obviously you have to understand what are the examples for each and every type of defect, right? You have to understand what are the examples, right? Now to this question, Z and S, will it show Frenkel defect? Interstitial is not show. Oh, okay, yeah, it is Frenkel defect. Okay, it is going to be Frenkel defect, right? Okay. Now, if at all anybody is not able to understand how is it Frenkel defect, like first of all, you have to know what is Frenkel defect, right? Then only the examples will come. Okay, right. Moving on to the next question. This is again the formula type of questions. Okay, fine. Now look at this. A structure of a mixed oxide. What is a mixed oxide, people? What do you mean by a mixed oxide? What is a mixed oxide? Anybody knows? Or can you give me any example of mixed oxide? Okay, so a mixed oxide is one which contains two metals. Okay, generally we write one metal, one non-metals, like say NaCl. This is not a mixed oxide, right? Generally, all the salts or all the compounds you will see are going to contain one metal and one non-metal, right? But if you take a mixed oxide, the example I can give you is NaAlO2, something like this. Now you see there are two metals here, sodium and aluminum, both are there, right? So these kind of substances are what are called as mixed oxides. Okay, so anyways, not important. So mixed oxide, the structure of a mixed oxide is cubic closed pack structure. Fine. Okay. The cubic unit cell is of mixed oxide is composed of oxide ions. Okay. 1/4 of tetrahedral voids. Again, a very important point. 1/4 of tetrahedral voids are occupied by divalent metal A, and the octahedral voids, all the octahedral voids, I didn't mention anything. All the octahedral voids are occupied by the monovalent metal B. Right? What is the formula of the oxide? Right? Now, you have to understand 3 points. First, where is oxygen present? Second, where is A present? Third, where is B present? Right? Now, A and B are very straightforward. They have told that A is there in 1/4 of tetrahedral voids and B is occupying octahedral voids, all the octahedral voids. Now, oxygen is the only confusion. They didn't give you properly what is this, right? The cubic unit cell of mixed oxides is composed of oxide ion. That means what? The entire unit cell, the lattice points, all the lattice points, right? All the lattice points in this is composed of oxide ions. Right. Now, please tell me, when I say CCP, what is the unit cell I'm talking about, people? What is the unit cell when I say CCP?
FCC, sir.
Exactly, right? You have to understand that when I say CCP, cubic closed pack structure, means I'm talking about FCC unit cell. FCC unit cell. Okay, right. Now we'll go to this. Before we move on, you have to understand how many tetrahedral voids, how many octahedral voids will be there in a particular unit cell. Okay, how many tetrahedral voids, how many octahedral voids will be there in a particular unit cell. Right. Now, this is the formula. This is a shortcut which you can remember. Right. If I have n atoms per unit cell, right, we know how to calculate n atom. How do you calculate this? N is very easy. You should take the contribution, multiply the number, you will be able to get what is the n value. Right. So if I have n atoms per unit cell, right, I will have n number of octahedral voids and 2n number of tetrahedral voids. That means what? If I find that there are 4 atoms per unit cell, right, I will have 4 octahedral voids and 4 tetrahedral voids. Sorry, 8 tetrahedral voids. This you have to understand. Okay, I think it's very simple. If I have n atoms per unit cell, n number of octahedral voids, and 2n number of tetrahedral voids. That means if I have, for example, 4 atoms per unit cell, where the n value is 4 now, right? So I will have 4 number of octahedral voids and 8 numbers of tetrahedral voids. Okay, 8 numbers of tetrahedral ones. Right. Now, this calculation of n value is very easy. Once you know what is the unit cell, you know what is the number of atoms per unit cell. Right. Now, I know in FCC, right, now all the 8 corners, right, the contribution is 1 by 8 and I have 8 corners. So I have 1, right, and also the face centers, right, I have 6. Okay, the contribution of each face is 1 by 2 and I have 6 faces. So this will become 3. So 3 plus 1 will become 4. Right. So I have 4 atoms per unit cell in FCC unit cell. Right. I have 4 atoms in FCC. Right. Now, what are these 4 atoms? In this question, if you check, in this question, you see the cubic unit cell of mixed oxide is composed of oxide ions. Means what? All the lattice points. That means the corner lattice points, the face center lattice points, all of them are occupied by oxygen atom. That is what they are trying to say. This entire FCC is made out of oxygen atoms. That is only in the lattice points. Obviously, in the voids, A and B are present. Okay, right. So can I tell from this calculation that there are going to be 4 oxygen atoms? Because I know in an FCC, 4 atoms are there. And in the question, they have mentioned that oxygen atom occupies all the lattice points in FCC. Right. So I can tell that there are going to be 4 atoms of oxygen in this particular unit cell. Done. So oxygen, let me write the ratio. O is to A is to B. O I have found out to be 4. I have to find for A and B now. Right. Now, any questions anybody has? Everybody's okay. What am I doing? What I'm doing here? Like, see, all you have to understand is when they tell it like this, it is composed of oxide ions, means what? Obviously, all the things are oxygen atoms. All the lattice points are oxygen atoms. Fine. Okay. Right. Now, I have found it at FCC. Now I found the number of atoms in the unit cell to be 4. So obviously I will have 4 octahedral voids and 8 tetrahedral voids. Now what are they telling in the question C? 1/4 of tetrahedral voids are occupied by A. Right? 1/4 of tetrahedral voids are occupied by A. So totally I have 8 tetrahedral voids. Right? Out of that, only 1/4 of them are occupied by tetrahedral voids. So can I tell 1/4 into 8 which is 2, is what is my A atoms. Right? That's what they're telling. I have totally 8 tetrahedral voids. Totally in an FCC unit cell, I have 8 tetrahedral voids. In the question, they are telling that I have 1/4 of the tetrahedral voids are occupied by A atoms. Right? So can I tell the number of A atoms in this particular structure is 2? Right? So now I can fill in the ratios. Now I'm going to put a 2 for A. Now, moving on. Moving on to B, they're telling octahedral voids are completely occupied by B. Right? It's not mental, it's metal. Right? Anyways, right? So all the octahedral voids are occupied by B. Now, how many octahedral voids I have? 4 octahedral voids I have. Right? And all of them are occupied by B. So I can tell that 4 Bs are there. Right? 4 Bs are there. So now I can put the ratio here. 4:2:4, or I can write what? If I write in terms of A:B:O, it is going to be what? 1:2:2. Right? I'm writing the A:B:O is 2:4:4. That will become 1:2:2. So now what will be the formula now? A:2:O2. Am I right? Is there any option like that? Yeah. A:2:O2. Can I get a yes from everyone? At least in the chat box, guys. If you understood, please type a yes. I'm looking at the chat box now. If there's any question, please ask. If there's no question, just put a yes. Okay. Go on. I have 22 participants. Please go on. Please. Quick, everybody. I just need to have a confidence that you understood, nothing else. Right? Okay. Okay, good. Very good. I hope everybody is following. I'm so happy. Right, good guys. Moving on to the next question. Right, ethylidene chloride. Right, ethylidene chloride is an what?
Geminal
Right.
dihalide.
Sorry?
Geminal, no, sir.
Wait for it. Now they are telling ethylidene chloride. I have only one Cl. Remember this. Okay, ethylidene chloride means I have only one Cl. Obviously, all the dihalides are out of the picture. Okay, all the dihalides are out of the picture because I have only one chlorine. If they have told ethylidene dichloride, then I should have thought about it. But now the dihalides are out of the picture because I have only one chlorine. Right. Okay. Now ethylidene is nothing but CH2 double bond CHCl. This is what is my ethylidene chloride. Okay, ethylidene chloride is this only. Right. Now we know that if I have a C double bond C, and if there is a functional group directly attached to the carbon having double bond, that is this carbon atom is sp2 hybridized. We don't have to go into details, but what you have to understand is if there is a functional group which is directly attached to a carbon which is having a double bond, this is what is called as my vinylic functional group. In this case, it's vinylic halide. Okay, right? So now that, please again, I'm repeating, right? So if you have a functional group, in this case, it is chlorine. If that chlorine is directly attached to a carbon which is having a double bond, it is called a vinylic halide. But say, if I have a C double bond C and there is another carbon next to that and that is having chlorine, now you see that this chlorine is attached to a carbon which is attached to a carbon which is having a double bond. Right, like this kind of structures you get, these are what are called as allylic halides. Okay, if the chlorine is directly attached to the carbon atom having double bond, vinylic halide. But if there is a carbon in between, that is carbon having the double bond and chlorine in between, I have a carbon atom which is not having a double bond, that becomes a allylic halide. Right, so can I conclude this question by saying that this is a vinylic halide because this is the structure? Right, I have a double bond, directly chlorine is attached. Okay, this is my vinylic halide. Good. Moving on to the next one. How many questions?
Sir?
Yeah, go on.
Sir, but in the textbook for vicinal halides, they give alkylid trihalides, and for geminal, they give alkylidine halides only, sir. For geminate, it was alkylidin halide, sir. Then ethylidin would be geminate, no, sir.
Okay, alkylidin, but they must mention dihalide, right? Okay, let me check this question. Okay. What happened? Why is it moving away when I write? What is wrong? Here's one moment. Let me close this again.
So, it's given, sir. Gem dihalides are named as alkylidin halides only, sir.
Alkylidin halides, geminal dihalides or alkylidin halides.
Vicinal only we get the prefix, sir. Ti we get prefix, sir.
Okay. Fine then. If that's the case, maybe the answer is. But the thing is, when I say ethylidene, it is containing a double bond, correct?
Yes, sir.
So if it is going to contain a double bond, it should be a vinylic halide. Okay, let me check. Okay, let me come back to this. Let me come back to this question later. Right. For now, okay. Now at least is it fine? Okay, great. Fine. Moving on to the next question. Because see, ethylidene means I definitely have a double bond for sure, right? So now directly chlorine attached. Even if you tell that okay, in the book if it is given like this, but I cannot deny the fact that this is a vinylic halide for sure. Okay, that means this question has two answers.
Sir,
that means,
sir, it's 1,1 chloroethane, no, sir. Ethylidene means.
Ethylidene means
1,1. We have 2Cl, no, sir, in the starting. Dichloroethane, no, sir. 1,1 dichloroethane only will get, no, sir. No double bond will be there, no, sir.
Okay. One second. I think what you are telling only is correct. Okay. But anyways, at the end of this class, I'll clarify this. Okay, just give me a moment. I'll clarify this. Okay, fine. Moving on to the next question. Right. To prepare alkynes containing odd number of carbon atoms, Wood's reaction is not preferred. To prepare alkanes containing odd number of carbon atoms, Wood's reaction is not preferred. Right? Now, why is it like this? Now, we'll try to understand what is Wood's reaction first. Right? Now, Wood's reaction, if you have 2Rx, right, and if you put Na in the presence of ether, not acetone, right, you are going to get RR plus 2 moles of NaX. Right. So now what you understand is if I have 1 carbon atom here, I'll get 2 carbon atoms. If I have 2 carbon atoms here, I'll get 4 carbon atoms. If you have 3, I'm going to have 6. Right. So all you're going to do is just, make it twice the number of carbon atoms compared to the reactant product. That is what you're going to do. Right. So obviously 3, 5, 7, all these are not possible. Right, because eventually you're going to get double it. You're going to double the number of carbon atoms. So definitely you cannot get any odd number of carbon atoms. Right. So that is okay. We'll understand why is it happening. We'll look at the options. Right. A lot of reaction mixture goes wasted. No. Right. A mixture of 3 different alkyl halides are formed. A mixture of 4 different alkyl halides are formed. A mixture of 2 different alkyl halides are formed. Alkyl halides?
Hydrocarbons, no, sir.
Yeah, like what do you mean by alkyl halides are formed here? Sorry guys, this is a wrong question. Okay, I will talk to epsilon people, right? This is absolutely wrong.
Sir, then by default we'll get 1 mark, sir.
Yeah. Don't worry about the mark, right? It's all about getting the clarity, getting the concept clear, right? This question is a wrong question. They said that they will send me the question paper before they send it to you, but they didn't send. I would have checked it if that was the case. Okay, fine. This question is absolutely wrong. Okay, we'll move on to the next question. Right.
So
in alkyl
hydrocarbon, then what would be the answer?
Even if all these are hydrocarbons, I am forming only one hydrocarbon, Kanna. See, there is only one hydrocarbon formed. I don't have any mixtures getting formed here. Okay, there is only one hydrocarbon. That's it. Right. Now, the correct answer to this question would have been it is based on the mechanism. That's it. Right. If you look at the mechanism, what is happening is, let me tell you this. Okay, it's very simple to understand. Right. I don't know whether I didn't teach you both of these chapters. I taught you only some other physical chemistry and T block. Anyways, so if you look at the mechanism of Wood's reaction, right, I have this Rx, correct, right? So what is going to happen is, I am going to have a homolytic cleavage, right? We know what is a homolytic cleavage. I'm sorry.
Yes.
Are you? Why are my arrow marks are so bad? Okay. Right. I'm going to have a homolytic cleavage of this bond. Right. So when I have a homolytic cleavage, I will have, obviously this will happen in the presence of sodium. Okay. This will happen. It will happen in the presence of sodium. So I will have R dot and X dot. I know these are free radicals, right? You all know that these are free radicals. Okay. Now I will have two such molecules, means two such R dot, two such X dot. Now these R dot and another R dot will come together to make R. That's it. That is the mechanism. Very, very simple. Okay. So the answer to this question, why, is because I will not be at all. It is all based on the mechanism. But I can have a variation of Wood's reaction. See, if I use the same alkyl group, obviously I will get only even number of carbon atoms. Okay, but look at it like this. If I have CH3Cl and if I have CH3CH2Cl, instead of using 2 moles of same compound, if I use 1 mole of 2 different alkyl halides and I put sodium in the presence of acetone, what I'll be getting, this would have been the free radical formed, this would have been the free radical formed. So you would have ended up with propane. But remember, this is not Wood's reaction. No. This is not Wood's. This is possible, okay? This is okay. This is completely possible, right? But this we cannot call it as Wood's reaction. Wood's reaction, I have to use 2 moles of Rx, same compound, right? But if you want an odd number of carbon atom, you can take 2 different alkyl halides and do the modified Wood's reaction and then get odd number of carbon atoms. That is okay, but we cannot call it as Wood's. Oh God. 1 second, guys. I have to mute myself. Something is going on. Just give me a minute. Okay. Right. I hope you get it. What I'm trying to say. Is it okay? Whomever asked the doubt, is it fine?
Yes, sir. Understood, sir.
Right. Okay. Good. Right. Going on to the next question. In alkyl halide, okay, we can look into the points. The carbon atom of carbon halogen bond bears a partial positive charge. Okay, fine. The halogen atom bears a partial negative charge. Okay. The carbon halogen bond of the alkyl halide is polarized. What is the answer to this question, guys? What is the answer?
All of these, sir.
Yeah.
Option B.
All of these. Yes. Now, see, they are talking about a CX bond. All other atoms are there with carbon. Okay. Right. So I have a CX bond. Now, please understand that there is difference in electronegativity, right? Because chlorine is highly electronegative, carbon is less electronegative than halogen, right? So there is always a difference in electronegativity when you have a CX, that is CL or CF or CI, whatever it is, you will always have difference in electronegativity, right? But if you understand that if I have a CC bond, right, there is no difference in electronegativity. Okay, so what is going to happen because of this, if you ask me, right? The consequence, like the students who have studied with me, we have done this so many times. What do you mean by a polar bond and all that? But students who are not there, I'm explaining them, right? Okay, so what happens here is, you know that in a covalent bond, 2 electrons are shared. 1 electron comes from this, 1 electron comes from the other carbon, right? Now, if you check, where is the electron density? Right, you will find that the electron density is exactly at the center of these 2 carbon atoms, is nucleus. Right, this will have a nucleus, this will have a nucleus. The electron density, you will find that it is going to be maximum at the exact center of these 2 nuclei. right? That means they are pulling the electrons towards themselves equally because they're equally electronegative, right? But if you go to a bond like this, not only this bond, any bond where you have difference in electronegativity, right? What will happen? We can easily understand that the electron cloud or the electron density is not going to be at the center, but since my X has more pulling power than carbon, the electron cloud will be more towards the higher electronegative atom. Again, I repeat, the electron cloud will be pulled towards the more electronegative atom just because it is more electronegative. How do you define electronegativity? We all know that it is the ability of the atom to attract a shared pair of electron towards itself. Maybe I should write. It is the ability to attract shared pair of electron towards itself. Right? Now you understand that this is the shared pair of electron we're talking about. Right? So since this has more ability to pull the electron towards itself, the electron cloud will be towards the halogen, away from carbon. So what is going to happen because of that? What is going to happen is, if this was at the center, there is no charge separation, right? But something negative, that is electron, is moving towards this particular atom. So this will have a partial negative charge. Why? Because I am neutral, something negative is coming towards me. Obviously, I'll write in a partial negative charge, right? So what will happen to carbon then? From carbon, the electron cloud is moving away, right? So obviously that will create a partial positive charge on carbon, right? And whenever you have this charge separation, you are going to call these kind of bonds as polar bonds, right? Not only this, the moment you see difference in electronegativity between the bonding atoms, you can call those bonds as polar bonds. Okay, I hope you understood how all of these are the answers, right? The carbon atom possesses a partial positive charge. Yes, we just saw, right? And then the halogen has a partial negative charge. Yes. Why all this happens is because the carbon halogen bond is a polar bond. Very, very simple. So all of these options are absolutely right. Okay, I hope everybody gets it. Moving on to the question. Methyl bromide, what is the time, people? Okay, fine. Methyl bromide is converted into ethane by heating it in ether medium with what? Now look at this. Methyl bromide, that is CH3Br, is converted to ethane by, oh, I'm sorry, this is Woods reaction, right? So maybe it's a mistake. It is not acetone, people, it is ether only, right? Okay, so now obviously this is Woods reaction, right? I have to convert CH3 and I have to make it twice the number of carbon atom. Obviously it is Na in the presence of ether. I told you it is acetone, please change it, I'm sorry, right? It is ether only, right? Okay, so it is going to happen in the presence of what? Sodium. This is nothing but your Woods reaction. Very simple. Moving on. The synthesis of 3-octane is achieved by adding a bromoalkane into a mixture of sodium amide and an alkyne. Right? The bromoalkane and the alkyne respectively are. Now look at this, please. Okay. Right. Now for you to understand this particular question, all you have to understand is, I have an Rx. Okay, now I'm talking about the nucleophilic substitution. Right? When I talk about a nucleophilic substitution, people, right? So this Rx, somehow, if I can produce another alkyl group which is having a negative charge, what will happen? The nucleophilic substitution can happen. Right? So that is exactly what are they trying to say. Okay, that is exactly what they are trying to say. Now, how can I produce this R minus? Right? That's a very good question. The source of R minus, okay, tell me one very good source for R minus, which you know. It is not based on this question, but I'm asking you, what is one very good source of R minus?
Hydroxide.
Hydroxide. Hydroxide. You should not tell hydroxide, you should tell alcohol. Hydroxide we use in inorganic chemistry. Okay, that's a very wrong word to use here, but still I understand what you're trying. You should tell alcohol. Okay, now if you see that here, now which is more electronegative? Oxygen is more electronegative. So if they undergo heterolytic cleavage, all I will be getting is R plus and OH minus. Where am I getting R minus here?
Okay.
Okay, right. Any others? What one amazing source of R minus? You all know it. When I tell you the answer, you tell, yes, sir, correct. Don't make yourself in that situation. Please, you yourself will tell me. Go on. I'll give you 10 seconds. Let me see who tells it.
Grignard reagent.
Very good. Very good. Who's that?
Akshayashri, sir.
Akshayashri. Very good, Akshayashri. It is Grignard. Right. I write RMGX. Now, how will I separate this? This is R minus and this is MgX plus. Very good. So now, if I make a reaction for you, say for example, if I had CH3CH2Cl and say if I go for CH3MgCl, which is my Grignard reagent, now what will happen? This CH3 will come and attack here and this chlorine will go. You will find that I'm going to have CH3CH2C. I'm sorry, CH3CH2CH3. Okay. This is again a nucleophilic substitution. This is one R minus which you can get, alkyl group which is having a negative charge, right? Now another thing is, I don't know why they gave you this, but still, right? Say if I have CH3, CH2Cl, and if I have any alkyne, right? Please understand, before we understand this, alkynes, not all alkynes, terminal alkynes, you must have studied this in your 11th class. Terminal alkynes are little acidic in nature. Is it not? CH triple bond CH can be written as CH triple bond C minus plus H plus. It is capable of giving me this H plus. Okay, it is capable of giving me this H plus, right? Fine. Fine. I can ask you a question, but I really don't want to waste time. Okay, I'll ask you this question. Why is it that this is possible? And why is it that when I have a CH2 double bond CH2, this will not happen? Why does it happen in alkyne? Why it does not happen in alkene or say alkane for that matter? Why? Any idea? At least students who have studied 11th with me should be knowing this. But again, it's 11th. Sorry. Anyways, go on. Any answers? Fine. Generally, in organic chemistry, how do you decide whether that particular acid is strong or weak? In organic chemistry, I'm asking. If I give you an acid, if I give you two acids, okay, how will you decide which is a strong acid and which is a weak acid?
Based on the dissociation of hydrogen.
Dissociates.
Based on the dissociation of hydrogen that we do in inorganic. Here also it is a factor, but that is not a major factor we look into.
Litmus, sir?
Yeah, go on.
Or litmus paper, anything?
No. Theoretically, I'm asking. That is experiment wise. Even if you do your experiment, whether it's a strong acid or weak acid, both will turn blue litmus red. Right?
So the range is there, no, sir?
Okay, fine. But okay, theoretically. So if I ask you, like say, if I give you HCOOH and CH3COOH, right? Like I'm not giving you any chemicals. I'm giving you only these structures, right? And in the exam, if this question comes, will you tell that, okay, I will take a bottle of HCOOH, CH3COOH, do the litmus test, and depending on the answer, I will.
Sir, it must separate into ions, sir.
Separate, obviously it will separate into ion. This will give me H plus, this will give me H plus, this will give me HCOO minus, this will give me CH3COO minus. Yes. Okay. Then
So the stability of the carbocation.
stability of the carbocation. If you are really near me, I would have thrown a duster at you. Carbocation. Where is the positive charge here? Where is the positive
No,
charge?
sir. I mean the stability of CH
What is it called as? Stability of what is this? What are these?
anions.
Okay, these are anions. Say a little more technically.
Carbonyl group, sir.
Carbonyl group. Talk with respect to an acid. Forget that these are organic compounds. After H plus, I removed a H plus. Something is remaining. What is it called as?
Acetate ion.
Okay, fine. Oh God.
Precipitate, sir.
See, I have an acid HA. Okay, some acid I have HA. I remove the H plus, and what is remaining is A minus. What is it called as? With respect to this acid, this A minus is called as
Conjugate acid.
wow, thank you so much. Conjugate base, right? Now, the answer to all the questions what I'm asking you is strength of an acid is directly proportional to the stability of the conjugate base. This is what you have to understand, and you will be using this a lot of times in your organic chemistry. At least in 12th, you'll be using it a lot. In alcohols, you'll study. In carboxylic acid, you'll use this. Okay, so the strength of an acid is directly proportional to the stability of the conjugate base. Right? Now, I know that this conjugate base is stabilized because I have resonance happening. Again, I have an R group. R can be H or any. Oh, God. It will take a minute. Okay, just a moment. Okay, fine. I'm so sorry, guys. Right. So, yeah, this statement, if you understand, right, the strength of an acid in organic chemistry decided by how stable the conjugate base is. Now, you see, this is resonance stabilized. That's why carboxylic acids are little strong acids. Okay. Now, coming back to this point where we started, where is it? Okay. I'm talking about this, right? I told you terminal alkynes are acidic in nature. It is because this is my conjugate base. After removing H plus, whatever is remaining is my conjugate base. This is stable. Now, can you tell me how this is stable?
Triple bond, sir.
So if I have a triple bond, what will happen?
Bond strength is higher, sir.
Bond strength is higher. No. You have to talk with respect to either inductive effect or resonance effect or hyperconjugation. Any of this, if you can remember anything, you can talk with respect to that. You can talk with respect to I, H, or R. Inductive effect, resonance, or hyperconjugation. What is possible here? Is resonance possible here? Forget about hyperconjugation. We don't have to go into detail. So either it is resonance or inductive effect. Can resonance happen here in this particular anion which I have? Yes, no. Okay, let me take a vote. Guys, go to the chat box and tell me yes or no. Resonance is possible means yes. If it is not possible means put a no. Go to the chat box. I'm looking at the chat box. Just type yes or no. Okay, not possible. Mokshit tells no. Others, go on. Everybody participate. It is not whether you want to know the answer or not. I just want to know what is your guess. Go on, only 2 answers, and I have 22 people here. Yes means possible, no means not possible. Yes or no? Quick. You just have to type 3 letters, and no means only 2 letters. Okay. Okay, go on, quick, guys. I'm looking at the chat box only. I think you can see my screen. I am looking at the chat box. Okay, so I understand that most of you are saying yes, right? Okay, I think I have another chat, right? What is it? Okay, can't yes. Right. Fine. So people, here resonance is not possible. How will you put the see? You already have three bonds, right? Now, if you make it come here, like let me draw it again for you. If I have, right now, I have this this thing. Say now, if this comes here, can you break this bond like this? This is a sigma bond. Can you break this bond like this? No. Remember, in resonance, I can play only with pi bonds, or in general pi electrons. Pi electrons means electrons in pi bonds in the form of negative charges, right? I have a negative charge, and this pi bond, how will you break? This you cannot break. You're making it, next bond you can break, right? But if I had something like this, if I had, right now here resonance is possible, because now say this will come here. Now I have a pi bond in the next carbon that can be broken. Now I can write the resonance structure like this: double bond CH2. Right? Hope you're all able to get it. Right here, resonance is not possible. Please understand. Okay. Right now, obviously, if resonance is not possible, obviously only inductive effect is possible. Right? Oh God, why is this happening today like this? I'm so sorry, guys. Right? This is really not expected to happen like this. Anyways, so now you understood that resonance is possible here, resonance is not possible here. So only by inductive effect, I'll be able to speak. Right? Now, you understand that I have a triple bond carbon, which is sp hybridized. Right? I have a triple bond carbon means obviously that carbon atom would be sp hybridized. Right? Now, remember, if I talk about electronegativities of carbon, sp hybridized carbon is more electronegative than sp2, which is more electronegative than sp3 hybridized carbon. Okay, sp hybridized carbon is more electronegative. What you have to understand is electronegativity is directly proportional to percentage of s character. Right, electronegativity is directly proportional to percentage of s character. Now you see in sp hybridization, I have 50% s. In sp2 you will have 33% S, right? And in sp3 you have only 25% S. I hope I hope you understand how am I getting these points, right? So more is the S character, more is the electronegativity. Okay, so now I told you that this is a sp hybridized carbon, right? So this sp hybridized carbon will be highly electronegative. So what will happen? It will pull the electrons towards this particular carbon only. So what will happen to the negative charge? Negative charge is decreased, right? Negative charge is decreased. And we all know charge and stability are inversely related. How? Obviously, a neutral species is more stable than a charged species. Positive, negative doesn't matter, right? A neutral species is obviously more stable than a charged species, right? So now with this analogy, I can tell a lesser charged species is more stable than a more charged. Like if I have higher charge, lesser charge is more stable because it is close to neutrality, right? So whichever is close to being neutral, that is more stable. Right now, here what is happening? Since I have a sp hybridized carbon, right? Since I have a sp hybridized carbon, which is highly electronegative, right? The negative charge on this carbon is decreased. So now the stability is increased, and that is the reason why alkynes, terminal alkynes, can give me H plus, because the conjugate base is stabilized by inductive effect. How inductive effect? Because I have an sp hybridized carbon, which is going to decrease the negative charge, thereby increasing the stability. Okay, right? I hope a lot of new things. These are not new, guys. These have been taught to you in your 11th class, right? So they're not very easy only, right? Now going back to the question, we actually deviated so much, but it's okay. You learned a lot of things. Now look at this: synthesis of 3-octane by adding a bromoalkane into the mixture of sodium amide and alkyne is what? What should be the bromoalkane? What should be the alkyne is what they're asking. Okay, now, right? So what am I telling is, if I have, say I write like this, RCH2Cl. Okay, now if I have this, say CH triple bond C minus, obviously H plus is gone. Okay, obviously H plus is gone. Now what can happen? Again, a nucleophilic substitution can happen, right? Now this can come and attack here, and this can leave. So what will happen here? R CH2 C triple bond CH. This would have been the product. Very simple, right? I just have to replace this with the entire thing here. That is the exact reaction what they're asking there also. Right. Now you understand that you end up with an alkyne. Right. Now they're asking here, I have basically bromine. What should be the bromoalkane? What should be the alkyne which is used for me to produce what alkyne? For me to produce 3-octane, octreine. Okay, so we'll check choice by choice. Okay, what happens? Now, what is the role of sodium amide here, if you ask me? Right. Now, please understand that if I have a C triple bond CH, and if I put the sodium amide, say in example, if I just put even sodium, now what is going to happen is, this is going to increase the dissociation to H plus. Basically, I will be ending up with C minus and Na plus. So this is more ionic. Right. Now, even though this H plus can come out, right, but the source which I'm going to have the negative charge will be more if I have an Na. This becomes a perfectly ionic compound, right? So that I can easily have this one attacking my substrate, attacking whatever the haloalkane I have. Okay, that is the reason why I have the sodium amide. Anyways, don't worry about this. Okay, now we'll directly see what can happen. I want to produce oct3-ine. Remember this. Okay, fine. Now look at this. If you take the option A, all you have to do is make the nucleophilic substitution reaction happening. Right now, can I say this will be the negative charge if you remove this H? Right now, if you attack, okay, actually, let me write this. But I have to clear certain things, but it's okay, fine. Right. Say now I write like this. I have CH3, CH2, CH2, Br plus, now this I'll write CH3, CH2, CH2, C triple bond C minus. Okay, now what will happen? This will come and attack here, and this bond would have broken. Now what you would have ended up with CH3, CH2, CH2. Okay, this part is done. Then come to this part. This carbon is attached to this carbon, right? This carbon attached to this carbon. So it will become C triple bond C CH2, CH2, CH3. Is it not? C triple bond C, CH2, CH2, CH3. Right? Now, what is the name of the compound you see? 1, 2, 3, 4. Or say if you start from this side, 1, 2, 3, 4. Now, this is oct 4-ine. Is it not? Because in the fourth carbon atom only, I have the triple bond. Right? Now, we will check for other things. Okay, we will check for other things also. How is it done? Right. Now, this I can for sure omit it. Why? Because you look at this, I have CH. Oh, no. This you cannot omit. Okay, this you cannot omit. We'll do this question also. Option B will check. Right. So if I check for option B, what I have to do now, this Br is gone. I have to write this. This Br is gone, and this carbon and okay, if I draw the structure properly, guys, it will be CH3, CH2, CH2. Now you see there are 3 CH2s. That's what they mean by this. CH2 thrice means 3 CH2s. Right? This is done, and I have a Br, and then I have what? CH3, C triple bond C minus. I remove the H. Okay. Now again nucleophilic substitution. What will you end up with? CH3, CH2, CH2, CH2. Now what? Now I have C triple bond C CH3. Right? Now C, where is my triple bond present? This is 1, this is 2. Obviously, I cannot go from this side. I have to choose the smallest possible number. Now this becomes oct 2-ine. Again, this is not the answer. Right? Now, if I go to option C, now let me check what happens here. I can directly write the product, right? If I write the product, right, it would be, I start from here. CH3. Now, how many CH2s? 1, 2, 3. CH3 thrice. Now, still one more CH2 is left. CH2. Now, you add this carbon because this is the negative charge. I have to remove the hydrogen. Now, this will become C triple bond C CH2 CH3. Right? I'm talking about C. Again, I repeat. I removed this Br and I attached this carbon to this carbon. Same mechanism only. Right? Now, check 1, 2, 3. Absolutely true. Now, this is what is going to produce my oct 3-ine. Okay, so the answer to this question is C. D, you don't have to check. If you check again, you're going to get something else. Okay, I hope everybody is following, even though we have learned acidic strength, like all these things. This is a simple nucleophilic substitution. That's all you have to understand. Right? I don't know whether this reaction is there in your textbook or not, but it's very easy to understand because I know alkynes are acidic. They can give me H plus and they can create a nucleophile for themselves.
Sir,
Right?
but there are 9 carbon atoms.
Okay, 1 second. Go on. What is it?
There are 9 carbon atoms.
There are 9 carbon atoms. Okay. How? 1, 2, 3, 4, 5. Oh, okay. See, this is also a confusion. Then that means this is not the answer. So then we have to check for this. Okay. Right. So if you check for this, definitely it would have come, right? Now you make this carbon attach with the third CH2, right? Let me, I don't have space. Right. But it will be very clumsy if I write it here only, right? Okay, let me rub this part. Okay, let me write here, right? Now you see, these are all the mistakes we easily do, guys. See, if I am able to do this mistake, definitely you will also do, right? So be very careful, right? Say this is all is for NCERT level. These are all questions. Fine. Anyways, okay. So now if I write this, right, it will be CH3. Now they told 3 CH2s, CH2, 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 and you have to attach this carbon here, right? This carbon is attached here. So you start 1, this one, triple bond, C, CH2. CH3. Yeah, this is the answer. 1, 2, 3. Yeah, 1, 2, 3, 4, 5, 6, 7, 8. Yes, this is oxygen. Okay, right. So first itself you neglect it. First you count the number of carbon atoms together. Whichever is making 8, that alone you check. Other things you don't even have to check. Okay, so this is the correct answer. D is the correct answer to this question. Right, guys, was it too much? Is everybody okay? Anybody wants me to repeat again whatever I told? Is there anybody like that? You can be free with me. There is no judgments passed. There is no criticism, nothing. If you want me to repeat, I will repeat. Is there anybody who wants me to repeat? Okay, I hope everybody is doing okay. Right. What is the time? Okay, we have 15 minutes only, but how many questions? So many questions are there. Oh my God. Guys, can we have a class during the weekdays? Can we have a class during weekdays? Say Tuesday or Wednesday. Will you guys be free? Yes, no?
Sir, math class is at that time, so Tuesdays and Wednesdays.
Math class is there. But I want to, if I have to discuss this. Fine, anyways, we'll see. I'll talk to Raghav. Let me see what I can do. Okay, fine.
Sir, you
So
can
next
post a
question.
recorded session, no, sir.
I can post a recorded session. See, if it's a recorded session, the problem is I will be explaining everything, right? I will not know whether you need this or not. Okay, it might be easy question and still I'll be spending so much time. And if it's a tough question, I might be spending lesser time, right? So at least once you are there with me, I will know, okay, students are understanding or students are finding it difficult, some kind of sense I'll be able to get. Okay, and I feel you are good at solid state, right? And you are not so good. I'm not talking about one person, I'm talking about the entire class. Okay, you guys are not so good in organic. A lot of basic things are not clear. That is why you're finding it a little difficult. Okay, fine. Let me see what I can do about this. Right, going on. The correct order of increasing reactivity of the CX bond towards the nucleophile. Right, now look at this, people. The correct order of increasing reactivity of the CX, this is the bond you're talking about, right? The CX bond towards a nucleophile, again, a lot of spelling mistake, in the following compounds is, right? Now we know generally, right, that haloalkanes, or in general, any benzene derivative, right? Any benzene derivative does not, or it's very difficult to make it undergo nucleophilic substitution, right? SN. Right? It is very, very, very difficult for the benzene ring, or not benzene ring, benzene derivatives to undergo nucleophilic substitution. I think in one of the discussion classes, we already discussed this. Some students were there, but most of you were not there. Anyways, right? Now we all know why is it like this, right? Because say, if I have chlorine, right? Now, if I have to substitute it with any other nucleophile, say a nucleophile is coming and I want to make this happen, right? This will not happen because I have a partial double bond character, is it not? If I draw the resonance structure, Cl plus and a minus, other things are there, and the resonance structure will keep on going, right? So what you understand is there is a partial double bond character because of resonance. Okay, that is why benzene and its derivatives will not, or it's very difficult for us to make benzene derivatives undergo nucleophilic substitution. Okay, but if I have the reactivity towards SN, that is nucleophilic substitution. I'm talking about only about benzene derivatives, guys. I'm not talking about generally. Right, it is directly proportional to the number of electron withdrawing group by resonance. I'm talking about resonance here. Right, it is going to be the more and more reactivity will be there if I have the number of electron withdrawing groups in the compound to be higher. Right now, why? What is the reason behind this is very simple. Right now, look at this. Right, if I have NO2, for example, right now, this is not an electron donating group. This is an electron withdrawing group. Right now, you see that this bond can go here, okay, and this bond can break. Right. So now, if I draw the resonance structure, it would be NO minus, and there's a coordinate bond, okay, and if this carbon would have had a positive charge, other things remain same. Right. So what will you understand is in the benzene ring fully, you will find only positive charges. But if you have an electron donating group like chlorine or OH or anything else, right, what you're seeing here, you are seeing negative charges throughout the ring. But if I have an electron withdrawing group, you are seeing that there is positive charge throughout the ring. Obviously, when I have a nucleophile, when I want to attack it here, obviously here it is easy, right? Because here I have a positive charge, positive, negative attraction will happen. But if it is going to go there, right, negative will try to repel. That is why when I have an electron donating group only, it is very difficult for the benzene ring to undergo nucleophilic substitution, right? But if I have an electron withdrawing group, that makes the reactivity higher towards the nucleophilic substitution. Right? Why? Because in the benzene ring, I'm going to have positive charges because of resonance. Right? Now, keeping that in mind, if I look at this question, right? Now look at this. Now compared to this is only X, there is no NO2, only one X is there. So obviously this is the least reactive because all the others are not benzene compounds. These are not benzene compounds. Right? And now you look at this, I have two NO2 groups. So definitely this will be more reactive than this because I have electron. This is an electron withdrawing group, which will increase the reactivity of the CX bond towards your nucleophilic substitution, right? And this question is, I would not say not correct, but information not sufficient, right? Why information is not sufficient is they should tell whether it is SN1 or SN2, right? Only then these two can be decided whether it's based on SN2 because it is neither SN1 nor SN2. This particular mechanism is entirely different, okay? Benzene rings undergoing nucleophilic substitution is an entirely different phenomena, entirely different mechanism. It's not SN1, it's not SN2. Okay, but if you look at these two, this is a tertiary halide, this is a secondary halide, right? Now, obviously, if it is SN1, this will be more reactive. And if it is SN2, obviously, this will be more reactive. So that should be mentioned in this question. Okay, they just told nucleophile, right? They didn't mention what is this, right? But if you can check the option, the least is 1, right? The least is 1. So I can blindly tell that A is the answer. Is it not? Right? Even though they didn't mention anything towards, but the correct question should have been, they should have included this SN1 or SN2, right? But they didn't include, but the options, if you look at the options, you can still answer the question, right? I know 1 is the least, and after that 2 should come. Definitely 3 and 4 are more reactive. Among 3 and 4, which is more reactive, is decided by SN1 or SN2. That is not given in the question. But option A, if you check, 1 is the least, then it should be 2, then 3 and 4 doesn't matter. We don't know about that, right? So I can blindly tell that A is the answer to this question. Okay, right? I hope everybody is following, right? Moving on. Okay, which of the following point defects are shown by AGBR crystals? Okay, AGBR, does it show Skotsky?
Yes, sir.
Okay, yes, it does show. Frenkel?
Yes, sir.
Yes. Metal excess, metal deficiency, I think no, they don't give, right? Right. So the answer would be A and B, and directly I can tell D, that is A and B is the answer to this question. Okay, fine, moving on. Which of the following is true about the value of refractive index of quartz glass? Now, this question is from isotropy and anisotropy. Obviously, right? value of refractive index of glass in different direction, a same in all direction, always 0. That obviously talking about directions of a particular quantity. Right. Now, quartz glass, is it crystalline or is it
Amorphous, sir. Amorphous.
It is amorphous. Okay, glass is an amorphous solid. Okay, so in amorphous solid, what is happening? Isotropy will happen. Is it not? Isotropy means irrespective of whatever the direction you are going to measure that particular quantity, it is going to give me the same value. Right? So can I tell B is the answer to this question? Right? Because it is showing anisotropy, the refractive index will be same in all possible directions. Okay, right, fine. Moving on. Chlorobenzene is formed by the reaction of chlorine with benzene in the presence of AlCl3. Which of the following species attacks the benzene ring? Very good question. Okay, for this, you need to know the mechanism of electrophilic substitution of benzene. Okay, fine. Like for this question, I tell you, hey, now look at this, people. I have benzene. Now somehow I have to create an electrophile. Remember this. Okay, somehow I have to create an electrophile that is having a positive charge, and obviously I have a hydrogen that will be replaced with this E, right? So I am going to get the E here. This is an electrophile. Okay, now, so obviously, you know, every time creating electrophile is a little difficult, right? Now, for that, if I have to make chlorine here, right? If I have to make chlorine here, that is, if I have to make chlorobenzene, right? Please understand that I need to produce Cl plus, not Cl minus. I need to produce the Cl plus, because remember, benzene and its derivatives will not, at least benzene for that matter, derivatives you leave. Benzene cannot accept a nucleophile, again due to the resonance structures. It can accept only an electrophile that is having a positive charge. Okay, so somehow you have to produce the Cl plus, and this Cl plus will attack. Okay, so answer to this question is very simple. The answer to this question is Cl plus. That's okay. But how am I going to produce the Cl plus is the question, right? It's very simple, guys. When I have Cl2 and Cl2, you make it react with AlCl3. Okay, you make it react with AlCl3. So what is going to happen is this CCl bond will undergo heterolytic cleavage. So this will produce Cl plus and Cl minus. Okay, now this Cl minus and AlCl3, remember the AlCl3 is a Lewis acid. We are talking about Friedel-Crafts reaction, right? Friedel-Crafts chlorination. That is exactly what we are talking about, right? So now AlCl3 will take up this charge, negative charge, to form AlCl4 minus. But this is not attacking the benzene ring. What is attacking the benzene ring? Whichever remaining, that is Cl plus which is remaining, that is only attacking the benzene ring. That is because benzene ring will undergo only nucleophilic substitution. That is what you need to understand. Okay, mechanisms are very important, but like NCRT is so pathetic that they are not concentrating on the mechanisms, but it is very important. Anyways, the answer to this question is Cl plus. Okay, next. Which of the following is the correct order of boiling point of the following? Right? So I have 1 bromoethane, 1 bromopropane, 1 bromobutane, and bromobenzene. Now all you have to understand is boiling point is directly proportional to molecular mass. It is inversely proportional to branching. Right? Now here there is no branching coming. Right? So the only case is molecular mass. Obviously, bromobenzene has 6 carbon atoms. This has only 4. This has 3. This has 2. So I can directly tell bromobenzene, bromobutane, bromopropane, and bromoethane is the correct answer. Yes. More boiling point. When will I have more boiling point? When I have more molecular mass and less branching. Okay, this is a very straightforward question. I calculate the molecule. We don't have to calculate the molecular mass. You know that bromobenzene has 6, the other has 4, 3, 2. Right? Definitely, you can easily tell that that is going to be having more boiling point. A is the answer to this question. Moving on. Arrange the following compounds in the increasing order of the densities. Densities say density is directly proportional to mass and it is inversely proportional to volume. Now, volume really doesn't make sense here, is it not? Because I know density is equal to mass by volume, right? So now we understand that volume has no role to play here. Forget about it. So density is directly proportional to the molecular mass. The mass which I'm mentioning is the molecular mass. So again, whichever is having the highest molecular mass, that is going to be having highest density. I think bromo, this one, Br is having more atomic mass, right? So D should have the maximum density. Then it should be C because it has 2 chlorines, but here I have 1 bromine and 1 chlorine. Here I have only 1 chlorine. I have there are no chlorines. So D should be maximum, A should be minimum. D should be maximum, A should be minimum. D is the answer to this question. Okay, right, very simple. Density is directly proportional to mass, inversely proportional to volume. Volume makes no sense here. Okay, moving on. What is the time? Okay, last question for the day, right? The order of reactivity of following alcohols with halogen acids. Right now, again, you cannot, just by looking at it, guys, you cannot know what exactly is happening. You have to know the mechanism. Let me tell you the mechanism. ROH, I am going to convert it into RCl, right? Now, obviously, I have to put H plus in the presence of H2O, aqueous acid. Right. Now, if you look at what is the mechanism here, ROH will first accept the H plus. Now, see, look at the arrow shooting. You should always put the arrow shooting from negative to positive. Negative only will attack the positive. Okay. In the benzene ring also, what I wrote is wrong, right? Benzene ring Cl plus, I told it's like, no, it should be this double bond is attacking the benzene ring. That is how you should tell. This is a wrong way, right? Negative to positive. Negative only attacks the positive. Positive doesn't move. Remember this. Okay. Positive doesn't move. Anyways, now going to this question. So this lone pair attack. So what will happen? I will form ROH2 plus, right? So what will happen now? This is basically water molecule. It will take up the lone pair. So I will form R plus H2O. Now comes your what? No, I'm sorry. I should have done HCl, right? Basically I should have done HCl in the presence of water. That is the correct thing here. So anyways, from HCl, H plus will come. That will attack. The same thing is happening. Then what is remaining now? Cl minus. Now this Cl minus will attack this R plus to form RCl. Right? Now remember, you cannot take directly Cl minus, attack here and remove the OH minus. You cannot do. Why? Why? Because there is something called as nucleophilicity. Right? Nucleophilicity means reactivity. How we talk about reactivity? Nucleophilicity is the ability of the nucleophile to be a nucleophile. How much ability it has. We don't have to go into the details. All you have to understand is OH minus is a better nucleophile than Cl minus. That is why if you have RCl and if I have OH minus, I can easily tell that this will come and attack here and this will go. I can form ROH. But if at all I have ROH, if you have Cl minus, you cannot tell that this is going to happen. This is absolutely wrong. Why? Because OH minus is a better nucleophile than Cl, so it will not be able to replace it like this. But if I compare the nucleophilicity of water and Cl minus becomes a better nucleophile. Okay, Cl minus becomes a better nucleophile. Now that's exactly what we are doing here. Now you see, first H plus attacks. I mean, the lone pair attacks the H plus. I am having OH2 plus. Now this now becomes a weaker nucleophile than Cl minus, right? So now once this leaves, I form a carbocation, then Cl minus will attack to form R plus. Okay, so the answer to this question lies here, right? The answer to this question is based on stability of carbocation, because you find that there is a positive charge on carbon, right? So it is all based on stability of the carbocation. Okay, now we all know that right? This, if I remove this OH and put a positive charge, remove this OH and put a positive charge, remove this OH and put a positive charge, can I say this is a tertiary carbocation? This is a secondary, this is a primary, and what is the order of stability? Tertiary is more stable than secondary, secondary is more stable than primary for a carbocation. So C is the one which is going to have maximum reactivity. Then comes B, then comes A. B is the answer to this question. Right now, I don't know why, like, did in the NCRT this mechanism is given, like whatever the mechanism which I wrote here is given to you. This mechanism, is it given? Guys, is it given to you, the mechanism in the book?
It's only given ROH plus HCl in the presence of
Sorry. What?
The only thing given is ROH plus HCl in the presence of ZnCl2 with RC.
Okay. See, you have to know the mechanism. Okay. If they are not giving you and they're asking questions like this, means they expect you to know the mechanism. Okay. This is a very simple mechanism, right? So first H plus attacks, then OH2 forms, then water molecule leaves minus H2O, forming a carbocation, then the Cl minus attacks to form RCl. Okay. So that is the answer to this question. Right, so C, B, A, because this tertiary carbocation which will form, this is secondary, this is primary, this would be the order of reactivity. Yes, any questions?
Yes, sir. In C, would there be steric hindrance, sir?
In C, will there be?
Steric hindrance.
No, that's what. Steric hindrance, we will not look into the picture because here it is not happening in one step. It is something like SN1, right? In SN1, how do we decide it? In SN1 reactivity, we decided by what? Stability of carbocation, because carbocation is formed. Right now, we know in this mechanism, I told you that a carbocation is getting formed, right? Right. If I tell you some other mechanism where carbocation is not formed, then you would have told me, sir, steric hindrance would also be a factor. But since here carbocation is formed, you have to talk only with respect to that. Okay, right? If it was SN2, yes, what you're telling is correct, but this is not SN1, right? This is something similar to SN1 because I have a carbocation formed. Okay, that is why we are speaking with respect to carbocation stability. Okay, Kana, understood?
Yes, sir.
Okay, so guys, we'll stop with this for today. I don't know how many questions are there totally. Oh my God. Is this the pattern, people? Will you have 55 questions to be solved in 3 hours?
1.5 hours.
1.5 hours.
My God. They are really making you suffer. I totally understand. Okay. Right. This is not fair on you. I totally understand. Okay. Fine. Anyways, let me speak to Raghav. Like, I will get a better clarity on this. Okay. This is not fair. I know, because knowing all this, sometimes you don't even know something is not given in NCRT and getting a question. Even in school, is it happening like this, people? Something is not given in NCRT and still they're asking you in the questions. Yes, no?
Till now, no, sir.
No. Okay. Right, but at least here, maybe only this question was like that. Other questions are fine. Okay, fine. Let me see what I can do about this. Okay, right. So I hope everybody is okay. Everybody is following. Something is there in the chat. Okay, fine. Let me stop sharing. Right. So I hope everybody got something out of this. Okay, don't worry, guys. Do not worry. Okay, this is just a testing phase. Right. You really don't have to worry about what are the consequences. It is really tough. First time we are talking about MCQs. Do not worry about any of that. You just prepare your science. Right. Concentrate on the science. Understand the science. Science will help you. Science, I'm talking about chemistry because I'm teaching chemistry, right? So believe in science, believe in the logics which you have, and you are going to do good. Trust me on that. Okay, fine. Thank you so much. You were a wonderful audience today. Thank you so much, people. We'll meet again. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, everybody.